My name is Terry, and in this video, I'd like to talk about double integrals and how to solve iterated double integrals. So we'll go through a review on the double integral concept, and we'll do two examples of solving iterated double integrals. So first of all, let's go back to Calculus 1, just so we can just have a brief review of the where the definite integral has come from. So from Calculus 1, we learned the area under the curve problem. So in concept, so the area under the curve, back in Calculus 1, we would use the definite integral to compute the area under the curve to the x-axis, and we would use it to compute the area under the curve of irregular shapes. So if you remember back in geometry class, you could find the area of a rectangle, base times height. You can find the area of a circle, area of a circle's pi times the radius squared, etc. But what if your shape is an irregular shape? We learned that we need calculus techniques to handle that. So I have an irregular shape sketched over here on the board. So to find the area of an irregular shape, where the concept here comes from, is when we started to learn this, we would take rectangles. We know how to find the area of a rectangle, base times height. We would take rectangles and inscribe rectangles inside the region. So if you took one rectangle and drew one rectangle under the curve here, base times height, it would give you an approximation for the area under the curve, but the approximation would be less than the exact area. If we inscribed two rectangles in our region, we put a rectangle here, a rectangle over here, we added up the areas of the two rectangles together, it would give you an approximation for the area under the curve, but it would still be less than the exact area. What if you inscribed about 10 rectangles, or whatever is here? It would be about 10 rectangles. Inscribe 10 rectangles, add the areas of 10 rectangles. Well, the area under the curve would still be less than the exact area. However, you are converging onto the exact area. You're getting closer and closer to it, but you're not there yet. So if you wanted to figure out what the exact area under the curve is, what do you do to figure out the exact area under the curve? We would need to use infinitely many rectangles, okay? So, and how is that possible, to add up areas of infinitely many rectangles? Well, it's possible. Once you learn calculus, you learn how to handle those kinds of things. So we would use infinitely many rectangles, and here's our equation here. So we're going to take the width times the height, is the width by the height is the area of the rectangle. We're going to use n rectangles in this region. We're going to let our n go to infinity. So this is our infinitely many. We're going to take infinitely many rectangles. We're going to take the areas of all these infinitely many rectangles, and what are we doing with these areas? Riemann sum, we're going to add them together. So you add up the areas of infinitely many rectangles, you will converge onto the exact area under the curve. Now, once you learn that, then the definite integral process, proven to be true through the ideas from the Riemann sum, the definite integral process, the integral from a to b over an interval of the function f of x dx, does the same thing. This will compute the area under the curve. So in Calculus 1, you learn this single integral. The single definite integral will work in a two-dimensional plane to find the area under a curve. So this is where this concept comes from. So now we move to Calculus 3. Calculus 3, you're really taking concepts from Calculus 1, and we're just taking all this, what we learned to do in 2 dimensions, and we're learning how to do all of these in 3 dimensions. Okay, so now we're in 3 dimensions, x, y, z plane, and we instead of a 2-dimensional plane figure, we have solids. We want to find, instead of the area under a curve, we're going to find the volume under a surface. We have 3-dimensional solids once you get to Calc 3. So 3-dimensional solids, and we want to go ahead and compute the volumes of the solids, okay? So, and you learn the concept of volume in a geometry class. You learn how to find the volume of a cylinder. Volume of a cylinder is pi times the radius squared times the height. You learn to find the volume of a rectangular prism, area of the base times the height. If it's a rectangular prism, it's length times width times height. Just find the volume of prisms and so on. What if this solid that you want to find the volume of is an irregular shape? So if this is an irregular shape, then we resort to our calculus techniques. So we want to find the volume under the curve. Well, instead, you can't use rectangles. Rectangles is a two-dimensional figure, so what we do is we have to use prisms. We're going to these boxes, we're going to put infinitely many prisms, same way that we did with the rectangles with Calc 1 class with the area. We're going to take infinitely many prisms. We're going to put infinitely many rectangular prisms under the curve. Okay. So and again, so how do you find the volume of a prism? It's area of the base times the height of the prism. So you have another dimension involved. So now we have base times width times the height instead of just the base times the height. So you have another dimension involved. So you can look at the Riemann sum defined formula to figure out the volume of a surface volume of a solid under a surface. And so when you look at this, here's your area of the base, okay, and then the f of x sub I of y sub I, this is going to give you the height of the surface, okay? So here's your area of the base and times the height, which is going to give you the volume. And you're going to take the volume expression, volume of all these infinitely many prisms, and what are we going to do with those? Riemann sum, we're going to add them together. And the extra Riemann sum is because you have a multiple dimension there. So, and then when you translate over to a definite integral, as we learned in Calc 1, you have a double integral involved, okay? So a double integral, so when you do integrate, you can only integrate one variable at a time. So when you get to Calculus 3, now we're in multivariate, so you have another dimension involved, so you have to compute a double integral. Okay, so and then the double integral, what this is going to do is it's going to compute the volume of the solid under the surface. That's one of the applications. There's so many different applications to this, but that's what we're going to be working with right from the beginning here. So that's the idea of double integration. So what I'm going to need to do now, let me go ahead and erase these. I'm going to erase the board. Let's do two iterated integral examples. Let's compute two iterated integrals so you can actually see how the computation of double integral works. So let me go ahead and raise the board. And okay, so our first example, we're going to integrate from 1 to 2, okay, so here's example number 1. So let's compute the double integral from 1 to 2, okay, for the outside bounds, okay, the inside bounds 0 to 3, so x squared times y, all right, so x squared times y, and let's go ahead dx dy. So let's go ahead and compute it this way first, okay? So the dx dy, that is our area of the base concept, okay? And then the x squared y, that is our multivariate function in terms of x and y. That is our function, that is our surface, okay? So that gives us that third, the height component. So here's the area of the base component, here's the height component, all right? So we want to learn how to compute, just compute an iterated integral. So you have two sets of integrals, you can only compute one integral at a time. So what you want to do is go ahead and start from the inside, one from the inside to the outside, okay? So we're going to start from the inside, we're going to go ahead and compute here first, okay? So we're going to go ahead and leave the integral from 1 to 2 on the outside. So integral from 1 to 2, okay? We're going to go ahead and compute the inside with dy. So don't worry what's out here, we'll take care of that shortly, okay? So, but you do want to integrate, let's just go ahead and integrate. Now we want to integrate with respect to x. With respect to x means hold y constant. Y is going to be held constant, integrate with respect to x. We integrate the x squared, we just carry the y with us. When you integrate x squared, that gives you x cubed over 3. Okay, and then bring the y, so x cubed over 3 for the integration of the x. Y is treated as a constant, so it's just going to be brought straight down because we're told to integrate with respect to x first, okay? And then we want to evaluate this expression. We want to evaluate this expression from 0 to 3. So let's evaluate from 0 to 3 using the fundamental theorem of calculus, okay? So we evaluate from 0 to 3. So you're going to integrate from 1 to 2. All right, fundamental theorem of calculus. Okay, if you remember, plug in the upper bound, all right, minus plug in the lower bound is f of b minus f of a, Okay, so here's a little template for the fundamental theorem of calculus. We're going to plug in the upper bound. Okay, now you're plugging in the numbers. You're going to plug in for the variable x. Remember, we kept y a constant. You brought the y down. Plug in the upper bound. So 3 cubed, so that's 27 thirds. So 9 times y when you plug in the upper bound. Okay, plug in the lower bound for x, and that gives you 0. All right. So here we are. After we evaluate this, okay, now we want to take this expression, we want to integrate this with respect to y, okay? So now we integrate with respect to y, so we integrate 9y with respect to y, all right? You're going to take the y, you're going to increment the exponent by 1, so you're going to end up with 9y squared, okay, over 2. So 9y squared over 2 when you integrate this, nothing to do with the 0 here. We want to evaluate this from 1 to 2. Okay, so we want to evaluate this from 1 to 2. All right, so the fundamental theorem of calculus says plug in the upper bound, and then subtract from that, plug in the lower bound. Okay, so we're going to plug in the upper bound, so 2 squared. Okay, so 2 squared is 4. 4 times 9 is 36. Okay. All right, so that gives us what, 36 over 2, so there's 36 halves, okay? Subtract from that, now plug in the lower bound, plug in 1, okay? So when you plug in 1, 9 times 1 squared, okay, so you got to square the 1. So 1 squared is 1 times 9 is 9, divided by 2, so there's 9 halves, okay? And then when you combine your fractions here, 27 halves, so 27 halves would be the answer, okay? So this is how you would compute an iterated double integral. This is how you would compute an iterated double integral. All right. Now, extending example 1, all right, just extending example 1, you could switch the order of integration, okay? You could switch when you have a continuous function. The x squared times y is a continuous multivariate function. There is a theorem called Fubini's theorem. It's on the screen over here. So Fubini's theorem says that if your f of xy, if your multivariate function is a continuous function over the given bounds given to you, over the rectangle given to you, so if you have a continuous function over the rectangle given to you, then it does not matter if you integrate the x then the y, or if you integrate the y first then the x, okay? So every once in a while, one way might be easier than the other. So x squared y, because this here is a continuous function over the rectangle given to us, then we could go ahead and switch the order of integration if we wanted to, okay? So switch the order of integration, okay, which means your multivariate function is x squared y, but instead of integrating with respect to x first, we could integrate with respect to y first, okay? So if we're going to integrate with respect to y first, we have to switch the bounds around. We have to bring the y bounds in. So we have to move the 1 to 2 bounds, because the 1 to 2 bounds are the ones associated with the y. Then we would integrate with respect to x, and we would have to just switch the bounds as well. So if you're going to switch the order of integration, which would work perfectly fine here, if you want to switch the order of integration, you would also have to adjust the bounds, right? So, I mean, if you want to see, okay, that it works, remember that when you're evaluating by hand, when you're evaluating the iterated double integral, we're going to work from the inside first, okay? So you work the inside first, so you're going to integrate from 0 to 3. And then now we integrate, okay, so we're going to integrate, but we're integrating with respect to y first, okay? Y is the variable, x remains constant, so we're just going to take the x squared, bring it down, because that's our constant. We're integrating the y. When you integrate y, that becomes y squared over 2. And we want to evaluate this from 1 to 2, okay? So fundamental theorem of calculus, and we'll take care of the integration with respect to x after this step, but we actually need to plug in and evaluate. So we need, and then we'll go ahead and integrate with respect to x, okay? So when we evaluate, you want to plug in the upper bound. Now remember, y was the variable here, so we want to substitute our constants in for y. 2 goes in for y. 2 squared is going to be 4. 4 divided by 2, 2, so this gives us 2x squared for this term, okay? Minus, then when you plug in the lower bound for y, you're gonna have x squared over 2. Okay, so you're plugging in the upper bound for y, plugging in the lower bound for y, all right? Now we can go ahead and integrate each of these terms with respect to x. We can integrate, so we integrate the 2x squared, you're gonna get 2x cubed over 3, okay? Integrate x squared over 2 with respect to x, you're gonna have x cubed over 6. Evaluate this from 0 to 3, okay? So plug in the upper bound, okay? So plug in the upper bound, so 3 cubed, 27 divided by 3, okay, is 9 times 2 is 18, all right? Minus plug in 3 here, so 3 cubed, 27 over 6, okay? So 27 over 6, all right? Plug in the lower bound, and you're going to have 0 minus 0, all right? And when you take 18 and subtract 27 over 6, 27 over 6 reduces to 9 halves. When you take 18, 36 over 2 is 18, and you do subtract 9 halves, you're going to get 27 halves for your answer, okay? And it works out either way, whether you integrate with respect to x, then y, or whether you integrate with respect to y first, then x. Either way, it works because you have a continuous multivariate function over the given rectangle. So by Fubini's theorem, just doesn't matter if you dx dy or dy dx, but you want to be careful because you can't always just switch the order of integration. But in this case, there's an example where you could switch the order of integration. So this is example 1. Computed an iterated integral. One more example, I'd like to do example number 2. Example number 2 is going to look a little bit different than example 1 because we're going to have constant bounds on the outside, but we're going to have variable bounds on the inside. We're going to have some variables involved, which means you won't be able to switch the order of integration. You would have to work from the inside to the out. So let me erase example 1. Let's take a look at example 2, computed an iterated integral where you have variable bounds involved. So let's go ahead and move this out of the way. All right, so example 2. Okay, so here we go with example 2. So example number 2, we're going to set up a double integral. The outer bounds will be from 0 to pi over 2. So let's go from 0 to pi over 2. And then the inner bounds are going to go from 0 to x. Okay? And let's go ahead and take x times the sine of y. Let's do something with trig here. We're going to dy dx. We're going to handle the y first and then the x. Okay? So we're going to do just dy dx for this one. All right? This is also an iterated integral. You have variable bounds on the inside, but it's set up for you, so all you have to do is just go through and handle the computation of it, okay? Outside bounds are constants. Your final answer is going to be a number. We'll see if we can get to that. All right, so here we go. So we want to start with the inside. You work from the inside to the outside, okay? So work from the inside when computing an iterated double, work from the inside to the outside. So you have 0 to pi over 2. Okay, we're going to integrate with respect to y. X is going to be held constant. Integrate with respect to y. So just bring the x down. Okay, and then when you do integrate sine y, the integral of sine y is going to be negative cosine y. So I'm going to pull the negative out front. So negative cosine y. Okay, so here's what we get when we integrate with respect to y. Okay, so integrate with respect to y first. X is a constant, bring the x down. Integrate sine y. The integral of sine y is negative cosine y. We want to evaluate this from 0 to x. The inside bounds is 0 to x. Okay, so we're integrating from 0 to pi over 2 on the outside when we get there. All right, fundamental theorem. So we want to plug in the upper bound. Okay, minus, and then we're going to plug in the lower bound. We're going to apply the fundamental theorem of calculus here, okay? okay? Plug in the upper bound for y. Y is the variable, so we're going to make our substitutions for the variable that we integrated with respect to. So we're going to substitute in for the y, substitute x in for the y, so you have negative x cosine x, okay? Now substitute 0 in for y, okay? You have negative x cosine of 0, all right? Evaluate each of these, make it a little bit, simplify a little bit, so you have 0 to pi over 2, okay? First term is negative x, the cosine of x, okay? Minus a negative, so that's a positive term, okay? Cosine at 0 is 1, okay? The cosine of 0 is 1, so you're going to have x times 1 when you compute that, okay? And now we want to integrate this with respect to x, okay? So I'm out of space here, so I'm traveling, okay? Traveling up to here, all right? So let's just resume, okay? So let me rewrite. I'm going to rewrite what I have here, right? But because I have two terms in the integrand, I'm going to go ahead and write it as two separate integral expressions. I'm going to split it up, okay? Because you're going to see that there's a couple of different techniques that we need to go over with the single integral. So we're going to integrate from 0 to pi over 2. All right, so we're going to integrate from 0 to pi over 2. First term, we have negative x cosine x dx, okay? All right, and then the other term is just x times 1 is x. So we're going to integrate this from 0 to pi over 2. We're going to integrate x with respect to x, all right? So just split it up just so you can see the two different techniques we're going to use here, all right? So the first integral, what we need to do to integrate negative x cosine x, we have to use a technique you probably learned in calculus too. It's called integration by parts to integrate this, okay? So integration by parts, so you have a product of two functions in the integrand, x times cosine of x. So integration by parts, when you have a u times dv, then you want to split it up to your u piece, your dv piece. There is a tabular shortcut method for this that I'm going to use here. So the shortcut to integration by parts, okay, so I'm going to make a chart with 3 columns. The first column is going to be SIGN, okay, to not mix it up with a trig function. SIGN, you have your u component, you have your dv component. All right, so SIGN, remember we always start positive when we alternate the signs, okay? Now u is going to be the algebraic in this example, so I'm going to call u negative x, okay? And then we want to find the du, we need to differentiate as we go down here, so negative 1, 0, and your v is the rest of the integrand, so it's going to be the cosine function, and we want to go from dv to v, so we want to integrate cosine. The integral of the cosine function is the sine function. Integrate that again, you're back to the negative cosine function, okay? So when you read your chart, this is a shortcut, your first term, okay, is going to be negative x sine x. This is how you read it. You go this way and you put these two terms together and you multiply. So positive sine times a negative x times sine x. So negative x sine x will be your first term with integrating this. So negative x sine x, okay? Your next term, let's see, we have a negative being multiplied by negative 1. That becomes positive, but then that's being multiplied by a negative cosine x. So your next term is negative cosine x, okay? So this is how you read, and then your third term where the 0 is, that's going to knock out. So we're done here. So we have the two terms. This is what you get when you integration by parts, okay? Now we want to integrate x also, just using the power rule, okay? So integrate x, that's going to be x squared over 2, all right? And so integration is done. Now we want to take this, we want to evaluate this from 0 to pi over 2. So evaluate this from 0 to pi over 2, okay? Fundamental theorem of calculus, okay, so we're going to plug in the upper bound, all three of these terms, plug in the upper bounds. You have negative pi over 2 sine of pi over 2 substituted in, minus the cosine of pi over 2, and plus you're going to have pi over 2 quantity squared over 2. When you plug in the lower bound, this term goes to 0 because 0 times anything gives you 0, okay? Cosine of 0, so minus cosine of 0, and then this term goes to 0 also, all right? So when you compute this, you have negative pi over 2, okay, times sine of pi over 2, which is 1, okay? The cosine of pi over 2 is 0, all right? When you take the pi over 2 quantity and square it, you're going to have pi squared over 4, and that's over 2, so this gives you a pi squared over 8. And then we do have a cosine minus a negative with a cosine 0 here, so minus negative, that's positive, and cosine 0 is 1, okay? So here, so your answer, I guess we can write it maybe pi squared over 8 minus pi over 2, and then plus 1, and here is the answer to example 2, all right? So your answer to example 2, so you've got pi squared over 8 minus pi over 2 plus 1, okay? So that gives you a little overview of double integrals, okay? Review of Calc 1 leading up to Calc 2 double integrals, and this is the process that you would go through to actually compute an iterated double integral. So this concludes this video. So, and thank you so much for watching. I hope this helps, and stay safe out there. Thank you.